In this video, we're going to talk about what I call ad hoc methods, which are the moving average and the exponential smoothing options that we have in the Data Analytics Toolpak in Microsoft Excel. Now, these are especially simple methods, and these are sometimes a little bit better for more long-run forecasting in relation to what we've seen in deterministic trends and seasonality. But these are especially adapted for irregular cyclical data. So things that don't have clear, say, linear looking or polynomial looking, perhaps quadratic or cubic, trends over time. Things that don't have clear seasonal patterns. Things that look, as I said, irregular but still smooth. So stock prices. I'm going to give you an example here that is, surprise, it's Tesla stock, and I've got closing prices. But as you see, it's smooth over time. It follows some shape of where it has been on previous days, and you might even jump and say that there should be some theoretical reasons why the best guess that you could give for the stock price today is whatever the stock closing price was yesterday. If you had some reason to believe that the stock price should be higher today than it was yesterday, then perhaps you should have bought it yesterday, which would have driven the price up, and over time, if everybody could do that, that would eliminate those potential gains. We have this idea that markets are efficient and it should be impossible to exploit them using information that other people don't have. It's something like that, our efficient markets hypothesis. Now, this smooth data isn't going to fit well to a linear time trend, and it certainly doesn't look like it has any sort of a seasonal component to it, even if you believe that you can buy and sell stocks at a certain time of year because they historically do worse over the summer or whatever your thought might be. That doesn't seem to be the case here. I don't see anything that looks seasonal, and I don't see anything that looks like a real linear trend, even though it has some shape. I would class this as irregular, and what I'm going to try to do is predict the stock price on every day using stock prices from the previous day, or perhaps an average of a couple previous days, such as these 3 days, to predict the next day, which is what a moving average will do. Or perhaps some sort of a convex combination of my previous forecasts and the most recent data in order to come up with a smooth picture of what this stock price should look like. So these are called ad hoc methods in my parlance because they're improvised. They're simple methods that just kind of work, using the last couple of observations from the dataset, if indeed those are the observations that have the most import in terms of value for predicting what's going to happen today, then using those last couple of observations is going to be possible in a couple of different ways, like smoothing together your most recent observation with your most recent forecast, which is what exponential smoothing does, or just taking an average of a couple of recent observations. So when I say they're improvised, I'm talking about simple, something that is a reasonable thing to do in order to try to maximally exploit the fact that this is a time series we're looking at, and it has these irregular time series components like this shape, whatever that is. I would also remark, because we had it right here, error terms that don't look random from the models we've been looking at in terms of deterministic trends and seasonality. When I see error terms that are correlated with each other over time from these other models, that's when I'm starting to think that there's some sort of an irregular cyclical pattern within the data, some sort of a cyclical behavior that a deterministic model like a linear or quadratic trend is not able to match. And these methods do, by, again, maximally exploiting just the time dimension that we're looking at here. Well, we'll start with moving averages. Moving averages are very simple, and the simple moving average, which does not involve any weights, you'll be interested to know that there are versions of this where, for instance, I put a parameter here, say theta, or I consider error terms from a model that's already been estimated, and I put parameters here and put different weights on them. There are more complicated moving averages and good ones, but a very simple way of doing a moving average would be take just the last k observations. This could be something like 1, 3, or 5, and add them up, divide by how many there were, just take the average of those observations and call that something like yt hat. Excel will do this for you, and that average is a very smooth version of what the data has been doing for the last couple of days. This might be a good way to predict what it's going to do today or tomorrow. There's an obvious caveat here, which is if my data that I'm using to create a moving average includes today, yesterday, and go back to K days ago, well, sorry, K minus 1 days ago, if I'm including today, then I'm clearly not going to use this average to predict today. So this YT hat might be useful as a prediction for tomorrow. That's what this is saying. Use YT hat to predict YT plus 1. Use the average of today and the last couple of days to predict tomorrow, and we could call that YT plus 1 given T. Again, this notation means the prediction you make for tomorrow using information up to time t. So this notation, where I predict tomorrow using information up to time t, is what I mean when I say that we're being maximally using the time series information. I'm using those last couple of observations from my data set because I believe that those last couple of observations have most of the information about where we're going to be, say, tomorrow. All right, that's the idea. Let me show you how to do this in Excel. I'll pop back to over here, and I'll get this picture out of the way. This is just what the closing price looks like. It doesn't look like a linear deterministic trend or any kind of seasonality that I can figure out. So I guess I'll go ahead and send that. Up here in the Data Analysis Toolpak, I've got all of my usual stuff, and there it is, moving average, something I never thought to use before. Input range, I'll go ahead and select this entire series of closing prices, and what I'm going to do is I'm going to give Excel the option to include whatever number of observations I think is best. So I'll say labels in first row because I did in fact choose the first row here. The interval is K, and if I just say 1, it'll simply give me the average of the last one observation, which is just the last observation. It's kind of an interesting model because I can literally predict tomorrow using nothing but what happened today. Well, I'll do a little bit more work than that this time, and I'll say my interval is 3. And output range, yeah, output range might be a good idea. Let's think about output range. I'll just put it here. Right, next to the original data. Why not? Well, all right, let's see what it did. So typically speaking, you might want to select this cell instead of that cell, and I need to go ahead and double click on this to verify that it did what I think it's going to do. It does give us the formula for what it's calculated, and you see that the cell I highlighted here as my starting value is maybe, okay, maybe I'm a column, maybe I'm a row away from where I want to be. I'll highlight all of this, Control X, and I'll paste it here. And then I'll look again and say, all right, first observation is simply NA, second observation is simply NA, third observation is, now we're talking average of these three. Is this the most consistent way of representing what we had over here on the slide? Let me see. The average at a given time, which would be a row in my Excel spreadsheet, should be 1 over K times the sum of the real data from that same row and the last however many, so that I have K of them. Yeah, sure enough, that's this, and I'll go ahead and call this MA3, which is essentially what I've done. It's a moving average of 3 observations. The 633 is the average of these 3, YT minus 2, and YT minus 1. This number here is the average of these 3. This is probably the way that Excel intends you to predict your MA numbers, or to use your MA numbers for output, where the YT at the average is adjacent to the most recent observation that is used to calculate it. I have a bit of a gripe with that from a forecasting standpoint simply because I can't use this number to predict 656. Why can't I use this number to predict 656? Well, because 656 was included when I calculated this number. So this number is actually old information. I would have these 3 observations when I predict the 4th one. So I would use perhaps this average of 3 observations as a stand-in for the 4th one when I predict the 4th one. For that reason, it might make sense to highlight this entire column and bump it down 1 more row so that I have essentially what actually happened and what I predicted. Now this is my MA3 forecast. All right, what actually happened and what I predicted being the average of my last 3 observations. With that, I can even come up with something like my MA3 error, which of course forecast errors are the difference between what actually happened and what you predicted. B5 minus C5 in this case. I hit enter and I see that my residual on this day was 46, meaning that the data was 46, the closing price was $46 higher than my forecast. And I can send that all the way down, scroll down to the bottom. Of course, this last one doesn't make sense because there was no observation there, so I'll eliminate that. And I can come up with simple statistics to tell me, for instance, how large this tends to be. I'm going to do that down here at the bottom. Say, what is my mean squared error? Okay, well, that would be equal to the average of all of these squared. I didn't calculate the squared errors yet, but is there a av? I've got average, average deviation. I have things like sum, which of course I could add them up and divide by how many there were. I have things like sum of squares returns the sum of the squares of the arguments. I'll use that one because I don't want to make another column for all of these. So I'll say it's the sum of these, row 254, all the way back up to, notice that I'm missing 3 of them here. So out of 254 rows, I've actually only got 250 observations in this column. So 250 rows by 1 column. If you're ever wondering how large the thing that you're highlighting is, I've got 250 observations in this. And then I'll close the parentheses, so this function will square all of those numbers, square the errors, add them up, and then I'll just remember to divide by 250. Look at that. I've got the formula for my mean squared error. MSE is 1895 for this data. All right. Well, let's try it again with a different lag length, a different number of old observations. Data Analysis Toolpak, moving average. I'm going to do the same thing, this data, but instead of 3, I'm just going to take 1 observation, and I'll put it over here in the next column. Oops. Not that output range, how about here? Okay. Oops. Don't like to do a moving average of just 1 observation, but that's trivial enough. So I'll do it from scratch. It'll be in this row equal to the average of this 1 observation. Instead of grabbing a group of 3, it's just 1 of them. Okay. And then it'll be 623 in the next row, and so on all the way down. And if I want to, I can say it would be NA in the first row. The NA, of course, means that in this case, there weren't 3 observations prior to put together, which is why I lost the first 3 rows in this data. But that's perfectly fine. My moving average of that number is going to be this number. And this 620 is a pretty reasonable way to predict the 623. It would just be a moving average of 1 lag. I'll go ahead and calculate my MA1 error to go along with that. So if I just use the average of the 1 observation most recent, then my error is equal to the difference between what actually happened, my closing price, and what I predicted. So minus my prediction for MA1. How big is my error term? Not bad, 2.88. And if I send that all the way down, then I see that, for instance, my error term was only 23.25 on the day where the MA3 model was 46. It's only $7.95 on the day when the MA3 model had an error of 18.5. So this looks pretty good. I'll scroll down to the bottom, remembering that some of these observations, if it had gone past here, would have been nonsense, but I'll calculate an MSE for this as well. MSE for these error terms, I'll say, is equal to sum of those squared errors. Of course, you could just say sum and square them if you want. I'm going from row 254 all the way up to row 3, which is 252 observations. Square those, add them up using sum square, and then divide by 252, which is how many there were. My mean squared error is 1256. Go figure. I just learned that, in fact, even though I gave you the formula here for a simple moving average with K, most recent observations included in the forecast, where K is larger, you'll get a smoother behavior for the series, but when K is smaller, sometimes you'll get something good. I have a smaller mean squared error. I actually have better predictions on average when I use only one of these lags to put together my moving average compared to using 3. If anybody, as an aside, if anybody's wondering why I'm using mean squared error, remember that mean squared error was part of the numerator in the formula for r squared. I'm not actually calculating regression models here, so I don't have r squared to compare, but I do have a mean squared error that I can easily calculate for any forecast just by looking at the real outcome that occurs and comparing it to the forecast. So that's what I'm doing. I'm calculating MSE, a smaller number is better. Neither of these models, the MA3 or the MA1, actually has estimated parameters. They're just model choices. And for good measure, I'll go ahead and do MA2. Since I'm so curious now, let's go ahead and hit the button over here. Moving average. Let's do 2. 2 is good. Labels in the first row. Okay. I will drop it here in column G. Drop it offset in. Nope. Clicked the wrong thing. So let's say close all the way to there. Good. Put these guys over here in column G. Not like that. Much better. And I have, let's see, once again, this is the average of the first 2 observations. So realistically, if I want my forecast to line up with the outcome, this number here in row 3 is really the forecast I would use for the number over here in row 4. I'm going to grab these again and just move them one row further down. Like that. How about like this? That's better. Okay. So the 622 could be used as an average of the first 2 observations. 622 could be used to forecast the 656. Well, all right. If you try, would my MA2 error be? Is equal to the difference between what actually happened and what I predicted. In this case, 34 and almost a third. I compare that to the MA1 error. It's a little bit worse, considerably worse, a little bit better again, a little bit better again. So it's worth asking, is the MA2 doing better than MA1? Let's find out. Scroll down to the bottom, and I'll do the same thing that I did in the other 2 cases. Trim these because they're out of sample. And then I will ask the question, MSE is equal to sum of the squared errors. Here are my errors. How many are there? 251. So I'll square them, add them up, and then divide by 251. Hit enter. 1538. Interesting. So uncorrected, mean squared error, all three of these. No degrees of freedom penalty. This one, MA1, actually did the best in this data. You may find that interesting because it's the simplest possible model you could ever imagine. Just use yesterday's value of the stock to predict today's value of the stock. And from these three models, that's as close as you can get. Okay. Next, let's consider exponential smoothing. This is a cute idea. Now, what exponential smoothing is going to do is saying your forecast for tomorrow that you will make today is going to be alpha. You'll notice there's a parameter here. Is going to be a little bit of the data from today, the model that we just looked at that was the best, that predicted tomorrow using today, or predicted today just using yesterday. Alpha is equal to 1. And then this other term drops out. So there is a relationship between what we're looking at here and what we had just seen. But this exponential smoothing says, I will predict tomorrow using data from today. How will I do it? Well, whatever happened today times alpha plus 1 minus alpha times the last prediction that I made, the guess I made for what would happen today using data from the day before. That's cute. Why is it cute? Well, your prediction influences the next couple of predictions. What you predict for tomorrow is going to be strongly influenced by what you predicted yesterday. But notice that the data enters in here. And so if you want this to be especially smooth, extremely smooth, such that today's forecast looks a lot like yesterday's forecast, and this is why it's called smoothing, then make 1 minus alpha large. You could call that a damping factor or a smoothing factor. And in fact, this 1 minus alpha is typically called the damping factor. What we have over here is usually called the smoothing factor. You could use either term because alpha and 1 minus alpha are obviously built on the same parameter. There's just an alpha. So if you know either of them, you know the other one. It's one of those things where we have two different names for the same kind of idea, kind of depending on which way you're looking at it. Now, Excel is going to talk about the damping factor, and it's going to ask us to specify a number for this, for 1 minus alpha. A lot of the other literature will talk about the smoothing factor, which is regular alpha, and of course this is different from our type 1 error alpha, but this alpha is typically a small number. We usually want this exponential smoothing to be very smooth, such that your forecast today looks pretty similar to your forecast yesterday. But we do want it to incorporate enough of this information from the new data that it behaves well. And depending on how noisy the new data is, a higher or lower alpha may be better. So something in the ballpark of 0.15 to 0.25 tends to be a well-performing number for alpha. I'm going to try 0.2 here in a second just to see if it works, because that tends to be pretty good. But Excel will ask me for this 1 minus alpha. Let me show you. Pop over to Excel. I've got exponential smoothing already highlighted here. I'll hit OK. Might as well scroll back to the top. And I've got a couple of different MAs already put in here. But what I'm going to do is ask for the same input range, which is closing prices. Damping factor is 1 minus alpha. I know that something like alpha equal to 0.2 is reasonably common or recommended, so I'll say 0.8 for the damping factor. I did include a label. And output range, well, let's just throw it over here and hit OK. Now this time, I made an extra row, and let me verify that this did what I think it would do. The first one is NA. Well, it makes sense that the first one is NA, because how am I supposed to make the first forecast from some observation without the previous forecast? I'm going to need some sort of an initialization step, and the most reasonable thing to do is just start off with regular old YT as your first initialization step, and then you can use that. When you do the next one, you can use that as yesterday's forecast. But I'm going to miss a row. And then here, okay, it's using yesterday's news, yesterday's actual price to predict today's price. So I see, in fact, this is my initialization step. This NA was looking for the previous observation, which would have been in row 1. So this NA is actually my forecast for row 2. I did put these in the wrong row. Let me fix them. I'll drop those right there. Now when I look at, I can also shrink some of these. Okay, now when I look at this row, my 620 is simply yesterday. This is essentially Y2, my forecast for time period 2, made using data from time period 1. But I initialized that state just by using the last observation. It's going to change when I double click on the next one. Watch. I double click on the next one, and what do I get? 0.2 times yesterday's data, which is 0.2 times yesterday's data. Notice this forecast is for tomorrow, or for today based on yesterday, or for tomorrow based on today. All right, so it's 0.2 times the most recent observation plus 1 minus 0.2 times the most recent forecast. All right, 0.2 times the most recent observation plus 1 minus 0.2, which is our damping factor, 0.8, times the most recent forecast. That gives me, notice, B3 is all past information, and I3 is all past information. So this formula is something I can calculate and use to predict what will happen in row 4. Right? Very important that my formula here only uses information from row 3, because I can only use information from today to predict tomorrow. I can't use information from tomorrow because it doesn't exist yet. I look at the next one and I see that row 5 is predicted using information from row 4, and row 6 is predicted using information from row 5, and so on and so forth. So let's not mess up any of those numbers. Now, these forecasts, 620, all right, so 620 was just what happened yesterday. I saw with the moving average numbers that 620 was a pretty good forecast, or at least the MA1 was a pretty good forecast. 621 as a prediction for 656, could be better. 628 as a prediction for 679, once again, could be better. So here's ES. My smoothing factor was 0.2. You could call it 0.8 if you're referring to the damping factor. And I'll say ES 0.2 error. What is it? Well, it's the difference between what actually happened and what I predicted. I was off by $2.88. So let me send that all the way to the bottom. Make sure I don't have any extras down here, and I'll do the same thing that I've been doing. The sum of the squared errors that I just calculated, and then I'll close those parentheses, divide by 252, which is how many there were, and that's not the sum of the squared errors anymore, it's the mean squared error, and I see that apparently this mean squared error is quite terrible. 3336 relative to the smaller mean squared errors that I had a moment ago with the moving average models. What I could do is I could try a different exponential smoothing model. So I'll do that. I'll say data analysis, let's do exponential smoothing again. Let's try, instead of 0.8 for my damping factor, maybe 0.85 is a little bit better. And output range, I'll put it over here. Hit OK. Once again, I see I've got it off from where I want it to be. I'll put it there. That's better. ES 0.15. I used 0.85 for the damping factor, so smoothing is 1 minus that, 0.15, and ES 0.15 error. Let's close that up. Here, my initialization step, of course, is exactly the same. Just use yesterday's data as your first forecast. After that, you can start smoothing together the most recent data and the most recent forecast according to this formula, the most recent data and the most recent forecast, to produce some smooth combination of those two. All right. What's my error? It's the difference between what actually happened and what I predicted on a given day. Send that all the way down, and some of them look terrible. I see a 50, I see some big numbers, but let's go ahead and try. And I'll make my mean squared error equal to the sum of the squared these errors all the way to the top, 252 of them, divide by 252. My sum of squared errors is now my mean squared error, and oh goodness, it's even worse. So it looks like out of all of these models that I just tried, the very best was actually the simplest possible moving average, a moving average with a lag length of 1. Let me unhide all the rest of those and scroll back to the bottom. And so sure enough, MSE, 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 and then a couple of MSEs for these two versions of exponential smoothing that I tried. 1256 was far and away the best of these lowest mean squared error. And who was it that generated that model, that MSE? It was none other than the MA1 model with no weights, just the simplest possible thing. So that's quite a radical result. It's not super atypical when we talk about things like the stock market, because again, we do have this imagined efficiency of the stock market. If you try this for other data, you'll have very different results. Now, we've only tried using these models for one step ahead forecast. Using these to predict 2, 3, or further into the future is going to require some recursive math, which is a bit of extra work, but there are some things we could put together there. In general, we do have some big statements about the exponential smoothing and the MA model. They're extremely simple. The exponential smoothing model only had one parameter. Now, if you have the opportunity to compare something like exponential smoothing or the moving average model to an autoregressive model or a deterministic trend model, using the mean squared error, which is easy to calculate using the regression output in Excel, it's pretty straightforward to see which of these is doing the best by comparing a statistic that you can compare across all of them. I recommend mean squared error. And generally speaking, these things do extremely well, in spite of being extraordinarily parsimonious. Why do they do so well in a time series? Because they're using the most recent data to predict the future. The most recent data has the most value in terms of predicting the future because it's the least removed from what is about to happen in the future. Now, this is just kind of a big overall statement about business data, but your most recent quarter is often the best predictor of what's going to happen this quarter, and this quarter is often the best predictor of what's going to happen next quarter, because there's no reason that information should jump across large gaps in time. Today is the closest you'll ever be to tomorrow, and vice versa. So extreme parsimony also makes these things great in really small samples. I can do things like moving average models or exponential smoothing in just a handful of observations, where things like seasonal factors for 12 months or large polynomials are going to become very expensive models to try to estimate in terms of potential overfitting. It happens that there's not a huge amount of theory supporting the use of these very, very, very simple models, but there is some. I mentioned the efficient markets hypothesis in terms of predicting stocks using just the most recent observation. In terms of using an average of several of the last few observations, that's not as well supported, but as we saw in that example, we didn't need them. And the simple theory for things like exponential smoothing, well, it makes sense that you would think about your most recent forecast containing a lot of information about the past because it was based on subsequent iterations of data, and your most recent forecast can be updated by looking at the most recent data. So there is some theory there. This is just kind of a general criticism that people throw at these models in terms of things like the weighted moving averages and autoregressive models that we see there's a deep mathematical theory behind those. The simple MA and the exponential smoothing that we looked at in this video are just very, very simple models that happen to perform well because they reflect the nature of the real world well. So that's all we have to say about these. I'll stop the video here, and I'll see you in the next one.